lab tomorrow involves making a serial adder. And there are a few things about it that are different. So up until now, your adders have all been like half adders or full adders, and you're kind of used to how they work. And then the serial adder works very differently. And I was in the class when he taught it, and I could sense from the questions people were asking that there was a little bit of confusion as to how it worked, which is understandable because it is a little bit different. But in addition to the actual serial adder being confusing, the way your lab is set up makes it a little, the display is not necessarily that intuitive as well. So let me explain what's going to happen here, and then we'll talk about the details. So if you look at the lab, it says, a serial adder performs binary addition bit by bit. It has two, okay, so that's a serial adder, and it does the addition bit by bit. Retains the carry out value to use as the carry in value for the next bit position. It performs the addition by adding each bit lowest to highest one position per clock cycle. In this lab, you'll create a Moore type serial adder. So what that part is saying is, if you have a number, let's say we have a 3-bit number, the way that you're going to add these with a serial adder is you'll have a serial adder, and I'm going to show you the setup that you'll be using, the way this is actually going to happen with your program, the way it's going to be set up. You want to think about your number as taking up these spaces, these bit spaces, and then you're going to have your sum, your answer, is going to be the same number of bits. And this one is going to be A, and this one is going to be B. And you have a serial adder that takes a bit from A and a bit from B and a carry bit. So when you start, your carry bit is going to be 0. So what happens is, in the program, you're going to shift each of these to the right. So A is going to become 1, 0, and B so A is going to become 1, 0, and the 1 got shifted out, and B will be 0, 1, and its 1 got shifted out. So I shifted both of those to the right, and then I'll add them to the carry that I have before, and I get an answer which is 0 with a new carry of 1, and I'm going to take that 0 and I'm going to stick it into the sum over on that side. So now the way it looks is I have A has a 1 and a 0, and B has a 0 and a 1, and I have a carry of 1. So now the next thing that happens is they shift again. So A is going to become basically 0, 0, 1, and you shift the 0 out. And B is going to become 0, and you shift the 1 out. and then you take those two numbers along with the carry that you produced last time, you give them to your serial adder, and your serial adder says, why, that answer is 0 with a carry of 1. So you hold on to that carry, you take the 0 and you take it over to your sum, and to your sum you shift what's already in there to the right, and you take your new value and you put it in on the left. And then in the last step, you're going to shift the 1 and the 0 all the way out. We had a carry of 1, so we'll add the 1 and the 0 together, and again we get 0 with a carry of 1. What numbers did I pick? I picked 5 and 3 to get 8. Of course I did. Okay, so you'll get we have a 1 and a 0 and a 1 that was the carry, so we get 0 carry the 1. So I take that last 0 and I shift these two to the right, and I take my last sum and I put it in here, and I get 0, 0, 0, because I picked two numbers that were too big to add using just 3 bits, because my answer is 8, which is 1, 0, 0, 0, which doesn't fit in 3 bits. But it did work the way it was supposed to. So that's the way your program is going to work. So you're going to be not just adding, you're going to be adding and shifting. And you're going to be shifting, different things in different places. So I wanted to give you that picture first. Okay, and now let's take a look at the description for the lab. It says, the textbook gives Verilog code for a Mealy type serial adder in figures 648 and 649. Write the Verilog code for a Moore type serial adder that adapts the Mealy Verilog code to include the following changes. So we're going to take the code from the book and we're going to adapt it. And as we adapt it, the adaptations we're going to make is we're going to use a Moore type serial adder. So the code in the book is Mealy. We're going to adapt it for Moore, and we're going to make the shift registers 4 bits wide. It's actually not that hard. One of the strange things about this is what you display, what your basis board is going to display. Your basis board is going to be displaying this sum as it's being produced. And so it's going to be kind of weird because it's not going to look like the number until you actually get it. So for instance, like let's say our numbers that we were going to add would be 0, 1, 1, 0, 1, 0, 1, 0. Okay, what is this first number in binary? 6, and the second one is? It's 10. I did it again. Let's make this just 4. 4 and 10. So we'll get 14. Okay, so what your lights are going to show is you're going to have 4 lights that'll be your sum that'll display. And when you add the first 2 bits, you would add 0 and 0, and you would get 0, so this light would stay off. And then when you'd add the next 2 bits, you'd get 0 and 1. This 0 would shift to the right, so it would stay off, but this light would light up. And then when you'd add this 1 and 0, you'd get 1. So that's supposed to be a lit. And so then everything shifts to the right. So now this is lit up, and now this is also lit up because it's a 1. And then when you do the last addition, you get a 1. So it shifts to the right. So this lit up shifts to there. This lit up shifts to here. And then this gets to here. And then you see that you've got 1, 1, 1, 0, which is 14, which is what you were supposed to get. So you see how it's building it up. So if your answer is supposed to end up being 0, 1, 0, 1, the sequence of lights that you're going to see, if you do it right, is you'll start off seeing, when you start, the first thing you'll see is a 1. Then you'll see nothing, so that's a light. I'll put a 1 for a light. And then that's going to travel down every time. And then you get a 0, and that's going to travel down. And then you get a 1 here, and that's going to travel down. So you would get 1 light, and then 1 light, and you get 2, and then you get 2, and then you finally get your answer. So it makes it kind of hard to debug to make sure you have the right thing. So you might want to be thinking ahead of time, have some things already worked out how you want to do them, because you're going to have A and B are going to be set up with switches. And so you might want to say, okay, well, if I have it switched like this, what are you going to expect to see when you press the button every time? You'll get a 0 the first time, so nothing, and then you'll get a 1, and then I think you get 1s from then on out. But I think, right? Because 0 carry the 1 is 1, carry the 1 is 1, carry the 1 is 1, carry the 1. Yeah. But it's going to be traveling down, and I can demo that before we leave, and I think I demo it in the video as well. All right, so now let's get to the worksheet. All right, so this is figure 648. This is the code for the shifter. So you're going to use this module as well as another module to put this together. So you'll be calling one module from another one. So this is shift right. Don't remember what the N stands for, and the E is the enable. But let's take a look at it. Okay, so it's shifting right. So the parameter says N equals 8. What do y'all think that N, what's the role of that N? Number of bits. So what are y'all going to use instead of 8? 4. Okay, then it has your input is R, and R goes from N minus 1 to 0. So if your N is 4, you can leave it as N, or you could just hard code it. You could put N equals 4, and then you could put this as 3 to 0 if you wanted to, or you can leave it as N. But 3 to 0, so that works. That gets us 4 bits. And then you have input L, E, and W, and clock, and you have your output Q is your reg. And W, so with the A and B in our example before, were we shifting anything into A or B? No. We were only getting stuff out. With the sum, were we shifting anything in? Yes, that's what this W is. The W is what you're shifting in. The W is what's going in when you shift something out. So for A and B, if we're using this module for A and B, what is W going to be for A and B? Always. It doesn't really matter, but I would make it 0. Because if you look at how we did it, I just left them blank as we were shifting stuff out. But if you're using that module, it's expecting a value for W to shift in. So the way the module works is you have however many bits you have, and it shifts them to the right, so each one goes to the one to the right, and then W goes into the blank spot. And we're using the same shifter for A and B and for the sum, so it's expecting a value for W. Yeah.
I'm sorry, just to double check I understand things. So what's going to happen is that we're going to basically add the least significant digit, then push the output into the first or the last entry.
The most significant bit.
Yeah, most significant bit. And then we're just going to keep on adding the bits with the carry included, and each time we just shift this number over, where the empty slots gradually get populated until the whole number is there.
And for the sum, and for the things we're adding, their empty slots keep getting emptier and emptier until they're empty, and then we're done. Because we're pushing stuff out of those.
Yeah. Like once we get to the least significant digit into the display's least significant digit, we're done.
Yeah.
That's what you're saying.
Yeah.
All right.
Yep. That's correct. Okay. So now back to the code. So W is the things that we shift in. Okay. So now look at number 2. Number 2 is if L, then Q equals R. And I'll give you a hint. The L, I think of something that stands for.
Light.
What's that?
Light?
Light? I wouldn't call it that. Okay, well let's move on. We'll come back to that. And it says else if E and then begin. So I've got all this business down here. Without looking at it too much, I can be pretty sure this is the shifting part. This is the shifting part, and my output is Q, and R is an input. So I think of L as load. So if load, then you make Q equal to whatever R is. R is you're loading that bit. So like we have to get a way to get A and B into the registers to start off with. So to start off with, we have to load them. So it's a parallel load. It's a parallel load, but a serial shifter. So if you tell it to load, then Q becomes equal to R, and that's going to be how you load your A and your B into your shifter. If you're not loading, then if E, you do this stuff. And what does this stuff do? Shifts. It shifts. And so I think of E as enable. So if enable, you're going to shift.
So you said W would be, you do W equals 0. You want to do that? Would you do it in a, like for the input, when we're shading inputs, would you want to do input W equals 0 or something like that?
Yeah, so like when I look at my code, let me look at my code real quick. What was the order? It was... Oh, I meant to stop recording. I wonder when I stopped recording.
Whenever you start looking at the code.
Okay, well that's okay then. All right, so All right, so E is for enable, and as long as it's enabled, it's going to shift 1. And so it's going to shift down to the last one. And then it'll put in to n minus 1 it'll put in that value W. So if we think about our 4-bit number that has n equal to 4, we start at n equals 3, and for n equals 3, so this goes, k goes from 3 as long as k is greater than 0, and then it says k of 2 becomes k of 3. So the value that was in 3 goes there. And then the value, and this is our whole for loop right here. And then n becomes 2. And so it says 1 becomes 2. And then n becomes 1. And so 1 becomes what 2 was. And then the end one becomes W. It's very important here that you use the non-blocking, because if you don't use the non-blocking, that might mess things up here, because you're changing the things, like if I change this right away, then that's going to be the same one that I'm going to shift all along. So you'll make sure you use those less than or equals. So if L equals 1, E equals 1, R equals that 8-bit number, and W equals 1 on the first clock cycle. So first clock cycle, we have L equal to 1. So what will happen on the first clock cycle? L is 1. So what did I say L was? The load. So on the first clock cycle, the load is 1. So what happens on the first clock cycle?
R gets loaded.
Yeah, R gets loaded. So Q becomes this number. On the second clock cycle, the only thing that changes is L equals 0. So now, if L is 0, what's going to happen?
For loop.
The for loop. And then it's actually, I don't know if this would actually be on the clock cycles or not, or if just the whole for loop. Yeah, it does happen on the clock cycle. Yeah. So,
It's always at positive.
yeah. So what's the next value going to be of Q?
Everything shifted 1.
Everything shifted 1. And then what's going to come in to take the place of the thing that, the empty spot? W, which is 1. Okay, and then what happens next with the for loop? Keeps going. And then it would just keep going. And my pen is not working.
Oh, it's one because W is one.
Because W is 1, and I'm not changing 1. I'm not changing W. I could change W, I just am not. Just like with A and B, I'm not changing W. W is 0 for them.
So basically, you'll end up with all ones.
And then you'll end up with all 1s. And just the same thing is going to happen to A and B. They'll end up all 0s.
I see. So whenever we count one sum, W will put the 0 in those boxes to the left.
Yes.
Okay.
Yes. So the way it's going to work for y'all is what those shifters are going to do is your shifter for A is going to, whatever you have in A, it's going to take the value that you have here and use it. It's going to send that to the adder. So that we haven't coded that part yet. It's going to send that to the adder. It's going to shift everything else to the right. And then because we put 0 in for what is going to be W, it's going to put a 0 there.
No, the last bit is a 1.
Is a 1, yes, should have been a 1. Because it sent the 0 to the adder. And then that's for A and B. And for the sum, it's kind of working the opposite. You're going to load it with all 0s, and then you're going to shift the numbers in the way you were describing. You're going to shift the answers that you get from adding in on this side. And notice that the first number you add are the least significant bits. You're putting them into the most significant bit. But by the time you're all done, that gets shifted down to the least significant bit. Yeah.
Sorry. Is there like a hardware reason that this is coded such that we're always like we're shifting number A, number B, constantly shifting the ones in, and basically I think we're ripping off the numbers we've already added. And then whenever we add the numbers, we're only adding the 0th, like the final bit. Is there any reason that we couldn't just use how like a always loop in as a parameter where we hit the button and it just reads the basically reads the bits that are being added as opposed to changing the initial or rather changing the QA, QB, shifting the numbers over?
So the answer to your question is kind of. There is a reason that you'll understand more about when you take microprocessors. A hardware reason, like you suggested, like how memory is actually read in computers. But the short answer to your question is, yeah, you could do this another way. But the lab assignment says we have to use the code that we're given. And the code that we're given has the shifter, and I can see very much why he would like this because he also teaches microprocessors, and it makes sense. Y'all do push and pop and things like that in your C++? Yeah. So stacks and things. I don't know. They're called different things in different languages, but yeah. So it's
Vectors and arrays.
yeah. So
First in, last out.
yeah.
First out.
Right, all that kind of stuff. And so that's the idea here. So this is a technique for doing it. It's not the only one. But it's the one that you're supposed to be practicing on this lab. Okay. All right, so here's the state diagram for a serial adder. Notice this one is a mealy adder, and you're supposed to do a more adder. So we're going to have to change this up a little bit. So the code that you have is the code that's in the book is written for a mealy, but we need to have a more. And the mealy only has 2 states, G and H. but we are going to have more states because we're more. Okay, so we have to figure out what those are. So let's take this problem here, problem 2, and use it to help us learn how this is working. So we have an initial carry-in of 0, which makes sense because when you start adding two numbers, you don't have a carry-in. Okay, and in this diagram, if you're in state G, that means your carry-in is 0. If you're in state H, your carry-in is 1. So when we start, we're in state G, and our inputs, state G, our inputs are 0, 1. So what's our output? It's just an adding. We're just adding 0, 1. 0 plus 1.
1.
Thank you. Okay, so our output is 1. All right. Now, if our input was 0 and 1, what's our next state going to be? If we're in G and our input was 0, 1. You can go back to G because our input was 0, 1. Okay, now our input is 1, 1. What's our output? 0. But we're now going to be going to a state, we're going to state H, which meant that we're going to have a carry-in of 1, because state H means your carry-in was 1. So now I'm in state H. My input is 1, 0. What's my output? 0. What's my next state?
Are we writing this for more?
No, we're writing for this machine right here.
Okay.
What's my next state? H. That means my carry-in is 1, because that's what state H means. Now my input is 0, 0. What's my output? 1. And what's my next state going to be? G, which means my carry-in is 0. Now my input is 1, 0. What's my output? 1. What's my next state? G, which means my carry-in is 0. And what's my next output? 1. So let's see if this worked. So we had 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1. And if you look, 1, 1, 1, 0, 0, 1, it worked. And notice, only at the very beginning when I asked y'all what's 0 plus 1, did y'all actually add. Every other time, you just looked at what the output was. But it worked. Because it's magic like that. Okay, so now we need to turn this into a Moore machine. I'm going to skip the next question I had on the worksheet in the interest of time. So how is a Moore machine different?
States are on the after the clock, or it changes output after the clock. Sorry, my brain's not working. What does it sound like?
So the the output depends just on what state you're in. So you just write your output right on the state. So we still have G, R, where your carry in is 0. And H is when your carry in is 1. And the output is written on the input. So if I am in state G0, that means my carry in is 0. If I get a 0, 0, where am I going to go? Go to 0, G0. If I get a 0, 1, is that going to give me a carry? A 0 plus a 1, does that make a carry? What's my output if I have a 0 and a 1? 1. So a 0 and a 1 or a 1 and a 0 will take me to G1 because I still don't have a carry. If I get a 1, 1, where am I going? To H0. Because 1 plus 1, my output is 0, but I am in the state where I have a carry. Okay, now I'm in G1. That means that I don't have a carry. It doesn't mean that I have a 1 hanging around somewhere. It just means my output was a 1 based on what I got last time. It doesn't mean I have a 1 sticking around anywhere. So if I get a 0, 0, where am I going to go? Back to G0. If I get a 0, 1, or a 1, 0, I'll stay in G1. And if I get a 1, 1, I'll go to H0. Now, if I'm in H0 and I get a 0, 0, where am I going to go? I had a carry of 1, and I'm getting a 0 and a 0. What's G1? What's 1 plus 0 plus 0? Yeah. 1 plus 0 plus 0 is 1 without a carry. What if I have a carry of 1, what if I have a 0, 1, or a 1, 0? Be back to H0. Because I'll have a carry of 1, so a 1 plus a 1 is a 0 with a carry of 1. What if I get a 1 and a 1? That'd be H1. Because a 1 plus 1 plus 1 is a 1, carry the 1. And then from H1, I'm going to go to the same places because H1 is not telling me, it's telling me I have a carry of 1 just like H0 did. So 0, 0 is going to take me here. 0, 1, and 1, 0 will take me here. And 1, 1 will take me here. So I will show you very briefly, I'll just show you one of them. So this is the adder part. This is the part that you're going to have to change the most from the code that you're given. So from the code that you're given, let's take a look at the code that you're given, which is right here. So the serial adder. So most of it is going to be the same. So you'll set it up, you'll change your numbers from 7 to 3. Oh, I do want to talk about this count. We'll get to that. You'll set up your shifters the same way. But the main part that you'll have to change is this adder part, because it's currently set up to be a mealy and you need a more. So this is going to be completely changed, this always block. So how are you going to set it up? Well, very similarly, we'll set it up with something like this. So you'll be getting the numbers from A and B. So you've popped out that number from A and B. And then Y is your state. Y is your current state. Capital Y is your next state. Since it's a more machine, you're going to have your case built on your Y. Now, in the code that you are given, you have parameter G equals 1B0, H equals 1B1. That's not going to work for you. You're going to have parameters G0 equals 2B00, G1 equals 2B01, H0 equals 2B10, H1 equals 2B11, because you'll have 4 parameters. So then, because it's more, once you know what case you're in, you know what your sum is. And so it's G0, so my sum bit is 0, so we know that. And then you determine what your next case is. So your next case is going to depend on what your values were from A and B. So we're getting that last value, that last bit of. That's why it's QA of 0 and QB of 0. We're getting that last bit, and we're looking to see what they are. Are they 0, 0, 0, 1, 1, 0, 1, 1? And these are the arrows on our diagram. So this corresponds exactly to the diagram that we just made right here. We had G0. If it was 0, 0, it went to 0, G0. If it was 1, 0 or 0, 1, it went to G1. If it was 1, 1, it went to H0. So what you will need to do is the same thing for the other 3 cases. So, so you have that. And then let's see what else we would need to change in this. Oh, okay, the count. Why is the count here a number that's from 3 to 0? What is the count even being used for? Let's look at this count. Where is it? It says if reset count equals 8, else if run count equals count minus 1, assign run equals vertical line count. Okay, this one, when I saw it for the first time for this lab, I'm like, what is this? Okay, so this is saying how many times do you need to get a number from your A and B. So this is your number of bits. So this count is your number of bits. So they made count 30 because they needed to be able to have a number as big as 8, and you have to have 4 bits to get 8. So you can leave it like this if you want. It's just you'll have extra bits. So this was just to be able to hold a number as big as 8. What will your count be? 4. So if it's at reset, you set the back to 4. You say, okay, you're going to go through, you're going to shift 4 times. You're going to shift 4 times, and then you're going to be done. Else if run, count equals count minus 1. So what this is saying is if run is equal to 1, subtract 1 from count. Let's see how this works. Okay, let's say count is 4. So count is 4, so count is 1, 0, 0. That's at the reset. So at the reset, we set count equal to 1. And then it says assign run equal to vertical line count. What that means is it's the OR of all of the count bits. So what's the OR of all of the count bits when run is 4? What's the OR of 1, 0, 0? 1. Okay, so now run equals 1. So when we come back to this one, we're not in reset. Does run equal 1? Yes. Run is 1, so it now makes count equal to count minus 1. Count minus 1 is 3, so 0, 1, 1. Run equals the OR of all of these bits. What's the OR of all of those bits? 1. And so it's going to keep going until you get to 0, 0, 0, and then run will be equal to 0, and then it'll stop going. Why did they do it this way? I don't know, but that's how they did it. It's just a new way of thinking about things, but it's the code that you're supposed to work with, so you've got it to work with. Do I have time? I do have time. Okay, so let me see if there's anything else I need to show you. I did not do the state diagram. I didn't show any of that. Okay, I kind of answered all of those things. I didn't do them directly. Let's see. So I said you need to change the parameters. You'll need to change these. You need to change those 7s to 3s. I would change this count to, I would change it to 1, 0. You don't need to have more bits because you only need to, no, you need 4. You need 2, 0, 2, 0. No, 4. Yeah, 2, 0, 2, 0. These are almost the same. This sum, you're going to change that to 4B0. You're going to completely change this. And I gave you the starter code for that. I gave you what to do for G0. You just have to do G1, H0. This always block will be the same. This always block will be almost the same. You just need to change that count to 4. So there's really not a whole lot to do. You need to map. Oh, that's why I made a separate video about mapping the switches. You'll need to map 4 switches to A, 4 switches to B, and 4 LEDs to, I think we called it sum. have on them a micro USB, or do I need to go run to my office? I'm going to stop the recording here because I don't have the camera on, so I couldn't just show the demo.